Hello everyone. In this video I'm going to explain why MOSFET is operated in saturation. Some of you must already be aware that if a MOSFET is operated in saturation, it can do something called as amplification. So let us see what actually happens if a MOSFET is operated in saturation and how it is going to do amplification. Let us just begin by defining few of the basic parameters. Like let us first define what is linearity. When you think of amplification, the first thing which you must know is linearity. Amplification and linearity are very closely related. Without linearity, we cannot call a process as amplification. So what is linearity? We can put a simple mathematical equation and see what linearity is. Let us consider this as a system whose input I feed it with some x, and if output y is equal to some factor alpha into x, where let's say this alpha is greater than 1. If a system can give such a response where output is nothing but input multiplied by some constant, it means the input and output are the same signal. You can see the x at the input is already there at the output, but multiplied by some factor. So this is a kind of linear relation between input and output. Even if I feed the system with, let's say, some x2, I will be getting some y2, which is equal to alpha into x2. Okay, so anything which I feed at the input, if it is the scaled version of the output. Also, if I feed sum of signals, for example, if I feed x1 plus x2 plus x3, and if the output is alpha plus x1 plus beta plus x2 and so on, if the system satisfies this, then we can call that system as linear. So to keep this concept simple, let us just capture this equation that input fed is x, and if output is some alpha into the same x, then we can call this system as linear. And if this alpha is greater than 1, it means output is greater than the input, and we can say it is doing something called as amplification. Okay, even though the actual definition of amplification can be much more complex, but I just want to explain what happens in saturation. Okay, let us just proceed forward. To understand this linearity even further, we can even talk about linearity in terms of graph. For example, if I take a system and feed it with a sinusoidal waveform, and if output is also a sinusoidal waveform but amplified by a certain amount, then we can say this system is a linear system. What we have to remember in linearity is the message is not lost. For example, I feed a voice signal, let's say this voice is some message. I do not lose the message out of the output. I get the same sinusoidal output, but it is amplified. For example, think of this system as a mic. Okay, if I say hello, I also hear hello, which is the amplified version of the input, but I must not hear hello with some kind of noise. So linearity is something like that. I hope it's clear. So any system which is able to do this, we can call it as a linear system. And by amplification, we also mean linear amplification, that is input and output are the same message, but the output is amplified version of the input. Okay, so if a MOSFET is able to do that, then we can use the MOSFET as an amplifier. Correct? Okay, so let's see if we can do that this process, that is feeding the input with some input with some signal and getting an output which is amplified version of the input. And if it follows the linearity, then of course we can use MOS as an amplifier. So let us take just a MOSFET. I have just taken NMOS as an example, and let's see what happens if this MOS, let's see if this can do, the MOS can do what is called as amplification. Now what I do is I connect the gate and source of the MOSFET with some voltage source, and the drain and the source with another voltage source. Okay, and Let's say what happens if I increase the gate to source voltage and keep the drain to source voltage constant. How does the waveform look like? Now if I increase the gate to source voltage greater than the VTH, which is the threshold voltage of the MOSFET, you will be able to see that there can be some current which flows from drain to source. Okay, until the gate to source voltage, that is this voltage, is greater than or equal to VTH, there is no conduction of current from drain to source. Graphically, you can it can be shown like this. Let's say there is no current here from this point to this. It means this is a point, let's say VTH, and once you increase the VGS above VTH, if you go on increasing, the current will rise like this, and any further increase in VGS, the current will increase linearly. Even though I have exaggerated this graph, it is not so linear. Okay, so just I have exaggerated the graph. You can see if VGS is increased beyond the threshold point, let's say this is the threshold point, the current, that is drain to source, the drain to source current varies almost linearly with respect to VGS. Okay, that is what we are talking about, right? The input is fed, and if the output is also the amplified version of the input, then we can call such a system as linear system, and also it can do amplification. On the other way, if let's say I keep VGS constant and if I vary VDS, we get another set of curve. Let the VGS be greater than VTH so that the channel is created and conduction of current can happen from drain to source. Now if I increase this VDS, you see that the current is increasing again linearly up to some value of VDS, and after certain point, that is if the drain to source voltage is greater than VGS minus VT, the current no longer increases, but you see it has saturated. It is no longer rising, it has saturated. And then any voltage greater than VGS minus VT, if you apply VDS, anything above this point, there is no increase in current. The current is almost like a constant. Okay, so what does this mean? If the VDS is increased beyond a certain point, that is if it is greater than VGS minus VT, the current is constant. Can you imagine of a device or let's say some component where it gives a constant current irrespective of the voltage across it? So that is what is happening here. Irrespective of whatever VDS I give beyond this point, the current doesn't change. So this is the definition of a current source, right? So it means that if you apply a drain to source voltage greater than VGS minus VT, from drain to source there is actually a constant current which is flowing, and then the drain to source current acts like a current source because it is independent of VDS. So what actually happened here? Now the thing which happened is the current which is flowing here between drain to source does not depend on the drain to source voltage, but only depends on VGS. This is a very good thing because MOSFET is a 3-terminal device, and if source, let's ignore source because it is kept common here, either VGS can change the current or VDS can change the current. If I'm able to make only VGS change the current, I get very good control of the output. So that can happen only in saturation. In saturation, the current doesn't depend on VDS, it only depends on VGS. Now let's say this is one set of current which you get for one value of VGS. What happens if you increase this VGS and again repeat the procedure of changing VDS? You will get another set of curve similarly like this. So for one value of VGS you get one value of constant current, but the condition is the VDS must be greater than VGS minus VT. So here is another example. If you feed this VGS by a higher gate to source voltage, so this second curve is for different value of VGS which is greater than the first value. So if I give a gate to source voltage, for every gate to source voltage there is one unique value of IDS which is constant, but the condition is you have to operate the MOS in the saturation. So the idea is simple. I feed the Mosfet with some gate to source voltage and I get a constant IDS. I convert the voltage into current, which happens only in saturation, and this current, which is constant, can be passed through a resistor, and then I can convert this current to voltage. So that is the basic idea about how we convert voltage to current using MOS in saturation and passing this current through some resistor, converting into voltage. I will just repeat the procedure. We have to first bias this MOSFET with fixed VGS and VDS. VGS and VDS must be such that the MOS operates in saturation. So the point of VDS must be somewhere on the straight line, and VGS can be any value, but it must be greater than or equal to the threshold voltage. Now once I operate my MOS in saturation, I can now feed some small signal to the gate to source voltage. These small changes which I apply to the gate to source voltage, which is the small signal, will create a small drain to source current here. Graphically it can be shown like this. This is my VGS versus IDS curve, and we know in saturation the current does not depend on VDS because it is a straight line here. Now if let's say this is your VGS bias point, if you now apply some variation in VGS, you can see because of the nature of this graph I get large value of current. So voltage VGS gets converted into IDS. But we have to remember that VGS, which is fed a small signal, must not be large so that I lose the linearity. Even though this line is completely linear, in reality it may not be so. Only if you apply a signal which is small, we can ensure that we are on the linear part of this graph. But if you increase the value of VGS, let's say increase from here to here, the line from here to here may not be linear. So VGS cannot give linear IDS if you feed a large VGS. This is how it is. I feed the signal VGS and I map the points. From this point I map here, from this point I map here. So every VGS, if I map onto IDS, this small VGS gets converted into large IDS. And if you actually see what value is this IDS, it will be GM times VGS. When this GM is something called as the transconductance. Now let us just look at some amount of mathematics. To start, this is the equation of the current if it is operated in saturation, where this K and dash, as in now, it is mu into Cox. VGS is a fixed gate to source voltage where it operates in saturation. VTH is a threshold voltage. W by L is the width and length. Now if I apply gate to source voltage, a small signal, I'm expecting a small signal change in the output current, it is small IDS. We have to now solve this equation on the right hand side. How to solve this? We know that this VGS minus VTH, it is a constant. So this can be taken as one parameter and VGS as another parameter. We can expand this equation as A plus B whole square, which is this term square plus this term square minus 2AB. If you expand it, this is how we get it. I am really sorry about this minus sign. It is supposed to be plus here because this is A plus B whole square. So this is A square plus B square plus 2AB. Now if you Bring this kn dash w by L and multiply with each term. The first term is kn dash w by L by 2 VGS minus VT whole square, which I think you know by now it is the bias current IDS. The second term is multiply this with VGS square, and third term is this is plus 2 into VGS minus VT. Now, so these are the three terms. This term, as you know, it is capital ID. It means this is not the change in the ID. These two terms are the small signal change. So the small IDS is this term plus this term. Now if VGS applied is very small, VGS square will become very small again. We can ignore this first term. For example, if I say, let's say it is 500 milli, or let's say 0.5. If I square that, it will become even lesser. So the first term can be ignored. So IDS can be approximated as kn dash w by L VGS minus VT into VGS, where kn dash w by L VGS minus VT is a constant, only VGS is a variable. So you can see IDS is equal to some constant into VGS, which is nothing but very much familiar, right? This is something which we discussed earlier. A system which is linear, if I feed x and if output is alpha into x, where alpha is some constant, we can call the system as linear. So you can see, because you operated the MOS in saturation, you applied VGS, which is equal to this x, and I got some constant into the same x, that is IDS. So this alpha is nothing but this kn dash w by L VGS minus VT. So this happened only in saturation, not in linear. The voltage VGS got converted into current, and that current is nothing but the input VGS into some constant, and this constant is kn dash w by L VGS minus VT. Let us see what is this constant term a little time later. So what we have to do, take a MOSFET, apply bias such that VDS is greater than VGS minus VT, operate in saturation, and VGS must be greater than VGS minus VT. Then once you are biased, at this point apply a small signal change in VGS. You will notice a large change in IDS, which is equal to this equation, that is small IDS is kn dash, this is plus, sorry, kn dash w by L VGS minus VT into VGS. Now we have to find out what is this term, what is this constant term. This constant term is a very meaningful term, which is nothing but transconductance. It can be very easily derived. This is the equation of the current in saturation. I differentiate this IDS with respect to VGS. So if I apply d by dou VGS on this right hand side, the only term which is VGS is this term. So if I apply dou by dou VGS, this will become 2 into this term, correct? So if I apply this entire term, that is kn dash w by L is constant, so I take it out, and in the differentiation of this is 2 into VGS minus VT. You can cancel this 2 and 2 and knock it off. This 2 and 2 gets cancelled. So this is what we get. So this term is kn dash w by L VGS minus VT, which is GM. And this is the equation which we just derived, that is IDS small change in current is equal to kn dash w by L VGS. And what is kn dash w by L VGS minus VT? We just derived it. It is equal to GM. This must be plus. So IDS is nothing but replace this by GM. It is GM into VGS. So if you see the entire equation flow and the graphical flow, this linear relation, that is this is amplification, the voltage gets converted into current multiplied by some transconductance. This becomes a definition of linearity, and if GM is greater than 1, obviously you are doing something called as amplification. So you convert VGS into IDS, that is GM into VGS. This is a plus sign, and then this current can be passed through a resistor and converted into voltage. So you bias the MOS in saturation, apply a small change in VGS, and the small change in VGS will be connected to IDS, and the output is given as GM into VGS. And GM is nothing but differentiation of IDS with respect to VDS. So this is the reason why we have to operate the MOS in saturation, so that it can do something called as amplification. We can convert voltage to current, and that current can be passed through resistor to convert into voltage. Graphically, if you apply VGS, at the output you get GM into VGS, which is VGS multiplied by some constant, and notice that output is a current, and current depends on the voltage at the input. So the drain to source current can be formulated or modeled as voltage dependent current source, because this current depends on the input voltage VGS. Okay, that's all I have. If you have any questions, you can drop comments in the comment section. Thank you. And if you have any questions related to this concept, you can always post a comment and I will get back to you. And if there is any videos in analog circuits which you want me to make, you can always drop me a message. Thank you for watching. Have a nice day.